All right, so we will go ahead and do this calculation to get the force between the Earth and the Moon using the universal gravitation equation. That's Fg. It's an attractive force, hence the negative sign. G, mass of the Earth, mass of the Moon, over their distance squared, and that'll be negative 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th times 7.34 times 10 to the 22nd. And we're going to divide that by the distance squared, which is 3.84 times 10 to the 8th quantity squared. So we'll run all that through the calculator, and we'll get our answer in a second. Times, I'm just running it through my numbers here. So I'm taking 6.67 times 10 to the 11th times 5.98 times 10 to the 24 times 7.34 times 10 to the 22 divided by 3.84 times 10 to the 8th squared. And I'm ending up getting about 2.0 times 10 to the 20th newtons. Now, the speed of the moon is in orbit Earth. This is interesting because what we're basically saying is the gravity force from Earth makes the moon orbit in a circle. And I'm actually going to do this problem using variables and plugging in numbers at the end. So I'm going to say that G, mass of the Earth, mass of the moon, divided by their distance squared, has the effect of making the moon move in a circle around the Earth. Now, it turns out the mass of the moon cancels from this equation. One of the r's cancels. So the speed of the moon about the Earth is actually given by G times the mass of the Earth divided by their distance under a square root. And when we actually work this out, that ends up being about 1,019 meters per second. Now, for number 3, we want to know what's the force on the ISS and the orbital speed of the ISS. I'm going to actually let you use these two things to help you set it up, but just so you know, when you're done, you should end up getting a force of about 3.65 times 10 to the 6th newtons. That'll be the force. And what you'll get for the speed is 7,733 meters per second. Okay, and the last problem is going to be deriving Kepler's harmonic law from the gravitational law of Newton. And again, we're going to talk a little bit about this next week, but basically what we're going to say is that Earth pulling on, or the sun pulling on a planet, obeys this gravity law of Newton that we talked about. And the effect of this gravitational pull of the sun on a planet is that the planet moves in a circular orbit. But circular orbit implies that the speed is 2 pi r divided by its orbital period. So when we substitute that into here, we're going to end up getting gm little m over r squared equals m times, and I'm going to factor out the m over r here, and then this v squared can be written as 4 pi squared r squared over t squared. Well, one of our r's cancels, the little m cancels, and so when we multiply both sides by r squared, what we'll end up getting is that r cubed over t squared is equal to g times the mass of the sun divided by 4 pi squared. Now, given the numbers that were given in this problem, one small thing is there's one unit conversion you need to do for the second part. You need to convert years to seconds. And to do that, you'll take the number of days in a year, times it by 24, and times it again by 3,600. When you do all that to get 1 year in seconds, and then you plug it into this formula here, you'll end up getting that the mass of the sun is about 2.0 times 10 to the 30th kilograms. So that wraps up our practice test, and I'll put these videos on Haiku so that you can actually go over the practice test on your own.